an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond.
While many think it's just a comet, some theorizing a possible alien origin due to a few curious characteristics.
This has been a really exciting time for astronomy, for astronomers, for physics. It's not too often that you get the world captivated on objects that may be suspicious, they may be malevolent, they may just be ordinary, and we may learn a lot about astrophysics along the way.
Object could be on a mission to release, quote, mini probes that could invade Earth.
Our best shot yet to clearly see the third interstellar object ever detected passing through our solar system.
The minimum size, it's supposed to be at least 33 billion tons worth of mass.
This camera was able to detect it, and what we see is a ball of light with a slight extension, it doesn't look like a typical comet.
Perhaps natural, but we should allow for the possibility that it's something else.
In a recent and remarkable finding, scientists have detected an interstellar comet releasing water vapor while still far from the sun, an observation that challenges long-standing ideas about how comets behave in cold space. The object, known as 3I Atlas, was observed by NASA's Neil Gehrels Swift Observatory, which detected ultraviolet emissions characteristic of hydroxyl, OH molecules, a byproduct formed when sunlight breaks apart water molecules. This detection confirms that the comet is actively releasing water even at a great distance from the sun, where temperatures are typically far too low for ice to sublimate. The phenomenon represents a level of activity never before recorded for an interstellar object, and it could provide important insights into how water and other volatile compounds travel across the galaxy. Comets are among the oldest and most pristine remnants of planetary formation, containing frozen gases, dust, and organic compounds that date back to the earliest stages of their parent star systems. When a comet from our solar system approaches the sun, its icy components heat up and vaporize, producing a visible coma and tail. But for 3I Atlas, this process is occurring at a location where the sun's radiation is too weak to drive conventional sublimation. The comet began releasing measurable quantities of water vapor at a distance roughly 3 times farther from the sun than Earth, an environment where solid ice is expected to remain stable and inert. For researchers, this anomaly raises new questions about the physical structure and thermal properties of interstellar bodies. NASA's Swift Observatory detected the unusual activity through ultraviolet spectroscopy. By analyzing the characteristic wavelengths of light emitted by hydroxyl radicals, scientists were able to infer the presence of active water release. This method has long been used to monitor comets within our own solar system, but its application to an interstellar object is unprecedented. The fact that Swift could detect these faint signals from such a distant comet demonstrates both the instrument's sensitivity and the strength of the emission. Calculations suggest that 3I Atlas is emitting approximately 40 kilograms of water per second, the equivalent of more than 1.36 times 10 to the 27 water molecules every second. Such a rate is extraordinarily high given the comet's distance from the sun and its presumed exposure to the harsh conditions of interstellar space. Even more intriguing is the proportion of the comet's surface that appears to be active. For most solar system comets, only about 3 to 5% of the surface is responsible for gas and dust emission. In Atlas, at least 8% of the surface is active, indicating extensive sublimation or ejection processes. This level of activity implies that a significant portion of the comet's outer layers contains volatile materials that are easily mobilized by even weak solar heating. It also suggests that the comet's structure may be more porous or fragile than previously assumed, allowing microscopic ice grains to be released and warmed individually in sunlight. The process thought to drive this distant activity involves microscopic ice grains embedded within the comet's surface layers. As these grains are ejected into space, they gradually absorb sunlight and warm up enough to sublimate, transforming directly from solid to vapor. This two-step mechanism could explain how the comet manages to release water at temperatures far below the usual threshold for ice sublimation. In effect, the comet is producing a delayed reaction in which material first escapes mechanically and then vaporizes once exposed to solar radiation. This phenomenon challenges current models of cometary physics, which have generally assumed that sublimation occurs directly from a comet's surface once it reaches a certain proximity to the sun. The implications of such a discovery extend beyond the behavior of one comet. By studying interstellar objects like 3I Atlas, scientists can gain new information about the distribution of water and organic molecules in planetary systems beyond our own. Interstellar comets are thought to be fragments ejected from other star systems during the early stages of planet formation. They travel through interstellar space for millions or even billions of years before being captured briefly by the sun's gravity. Each of these visitors carries chemical fingerprints of the environment in which it formed, providing a rare opportunity to study extraterrestrial material without the need for an interstellar mission. 3I Atlas is only the third confirmed interstellar object ever observed, following Oumuamua in 2017 and Comet Borisov in 2019. Each of these discoveries has provided a new piece of the puzzle regarding how material circulates through the galaxy. Oumuamua was dry and rocky, lacking any visible outgassing, and appeared to be composed mainly of dense refractory material. Borisov, by contrast, displayed strong emissions of carbon monoxide, suggesting it originated from a colder, more volatile-rich region. Atlas, with its unexpected water activity, occupies an entirely new category. It demonstrates that interstellar comets can remain rich in ice despite long journeys through the harsh radiation of interstellar space, implying that such materials may be more common and more durable than previously believed. The activity of Atlas provides valuable clues about how easily accessible ice and dust grains behave when exposed to sunlight at great distances. The temperatures at its observed location are far too low for conventional vaporization, which makes the presence of water vapor a clear sign of fine-grained material being released and gradually warmed. Scientists studying this behavior believe that Atlas's outer layers may have been disturbed either by internal gas pressure or by mechanical stress during its entry into the solar system. The resulting emission of ice grains could create the observed halo of vapor as those grains sublimate over time. This discovery not only expands our understanding of cometary physics, but also challenges previous assumptions about how heat, radiation, and sublimation interact in the cold outskirts of star systems. Beyond the immediate physical explanation, the discovery has profound astrobiological significance. Water is one of the fundamental ingredients for life as we know it, and understanding how it moves through the galaxy is key to understanding how habitable planets acquire their water. Interstellar comets such as Atlas may act as natural transporters, carrying water and organic compounds from one planetary system to another. Over cosmic timescales, impacts by such bodies could deliver these essential elements to young planets, setting the stage for the emergence of life. The idea that the water on Earth, and perhaps even some of the organic molecules that led to life, could have originated from material ejected by other star systems has gained increasing support in recent years. Atlas offers a living example of how such a process might occur in real time. Spectral analysis of 3I Atlas reveals another intriguing detail. While it is rich in water, it is poor in cyanogen, CN, a compound that often serves as an indicator of carbon chemistry in comets. This chemical signature suggests that Atlas formed in a carbon-deficient region, possibly around a young metal-poor star. Its composition sets it apart from not only solar system comets, but also from its interstellar predecessors. Oumuamua showed no significant volatile emissions, while Borisov was abundant in carbon monoxide. The chemical diversity among these three interstellar objects underscores the wide range of planetary formation environments that exist in our galaxy. It also hints that the processes that produced our own solar system comets may represent just one of many possible pathways. Such differences highlight the importance of interstellar comets as samples of other worlds. By examining their composition, scientists can infer the chemical environments around distant stars, regions that are otherwise beyond direct observation. The discovery that Atlas is both water-rich and carbon-poor adds a new dimension to our understanding of galactic chemistry. It suggests that some planetary systems may favor the formation of oxygen-bearing compounds, while others may produce carbon-dominated materials. These variations could influence the likelihood of forming habitable planets or even the types of life that could potentially arise there. If water-bearing comets like Atlas are common throughout the galaxy, they may play a crucial role in distributing the building blocks of life across vast distances. Research already indicates that Atlas is not just a singular object, but part of a class of interstellar bodies that enter our solar system. Every interstellar comet we study tells a different story, with the valuable insights developed by Zexi Xing and the team responsible for analyzing the SWIFT data. Others noted that Atlas's distant water activity is especially informative because it defies the thermal limits expected from standard cometary models. The team's work demonstrates that volatile materials can survive interstellar travel and remain active under minimal solar heating, suggesting that the early stages of planetary formation across the galaxy may be more efficient at preserving such materials than scientists once thought. The findings from Atlas may also prompt a re-evaluation of how common habitable materials are in the Milky Way. If interstellar comets frequently contain water and other volatiles, then the conditions necessary for life may not be rare or localized, but instead widely distributed. Each of these objects becomes a small-scale probe of another solar system's chemistry, carrying information about its environments that cannot be studied directly with current telescopes. In this sense, interstellar comets are messengers from other worlds, fragments of alien systems passing through ours, offering fleeting but invaluable data about the broader galactic ecosystem. Looking ahead, scientists view 3I Atlas as more than just an isolated discovery. They see it as a stepping stone toward a deeper understanding of how planetary systems exchange material across interstellar space. Each interstellar comet that enters our solar system carries information about its place of origin, its star, its chemistry, and the processes that shaped it. Studying these visitors offers an unprecedented opportunity to piece together a galactic narrative of matter migration, how dust, ice, and organic compounds travel from one stellar nursery to another, seeding new worlds with the ingredients for planets and potentially life. Future missions could one day go beyond observation and move toward direct interception of such interstellar bodies. Concepts already proposed by scientists involve launching fast-response spacecraft capable of adjusting their trajectory within days of an object's detection. These missions would aim to rendezvous with or fly through an interstellar comet's coma, capturing microscopic dust and ice particles for return to Earth. Analyzing these materials in terrestrial laboratories would allow researchers to measure isotope ratios and molecular compositions in extraordinary detail, determining not only the comet's chemistry, but potentially identifying the stellar system where it formed. The isotopic fingerprint of elements like hydrogen, oxygen, and nitrogen can differ subtly between star systems, offering a kind of cosmic identification tag that could, for the first time, link a physical sample to another part of the galaxy. Such a mission would be among the most ambitious ever attempted. The technical challenges are formidable. Interstellar objects travel at immense speeds, often exceeding 50 kilometers per second, and their discovery usually occurs only weeks before their closest approach to the Sun. Intercepting one would require rapid detection systems, autonomous navigation, and propulsion technologies far more responsive than those used in traditional deep space missions. Concepts such as solar sails, ion drives, or even nuclear electric propulsion are being studied for their potential to chase or match the trajectory of such fleeting targets. If achieved, the scientific payoff could be enormous. A direct examination of material that formed around another star, preserved for millions of years in the cold vacuum between systems, and delivered to our doorstep by chance and cosmic motion. In the end, 3I Atlas is not just another comet passing through the solar system. It is a representative of a distant and unknown origin, carrying within it the chemistry of another star. Its emission of water vapor from such a remote location defies expectation and reveals a universe more dynamic and interconnected than previously imagined. The detection of hydroxyl signatures from this lone traveler demonstrates that even in the cold and empty stretches between the stars, water, the molecule so essential to life, persists. As scientists continue to study this remarkable object, they are reminded that the story of life's ingredients is not confined to one world or one sun. It is a galactic story, written in ice and dust, carried silently by comets like 3I Atlas across the endless sea of stars.